Now, in the first part, we only considered the properties of the membrane themselves. Now we're concerned with the combination of the membrane and the conductivity of the body of the cell, the axon itself. The model that we come up with is the so-called Hermann cable, which actually is equivalent to a description of a coax cable in electronics. Now here you see the equivalent circuit of such a Hermann cable. Every small piece of the axon membrane and the piece of the axon is characterized by this membrane circuit of a parallel connected resistor and capacitor, yet on top also a voltage source, which is described by the voltage across the membrane. Now those little pieces, for example in this dashed box, are connected through the cytosol, which is characterized by an internal resistance dr and also an outside resistance, where we assume that the outside resistance, because the axon is lying in a very big volume, is 0. Now again, a recap on the different parts. So there is an internal resistance, or the core resistance, which is called Ri, given by the volume resistance of the axon, which is in the order of 30 ohm centimeter, divided by the surface of the axon, which is pi r squared, where r is the radius of the axon. Typically, this is 1/4 of a millimeter. Then there's the membrane resistance, Rm, characterized by rho divided by 2 pi r, or if we relate the membrane resistance to the internal resistance, that is given by rho divided by 2 rho I times r. Hence, the larger the radius, the more important gets the membrane resistance. Now the third component is the capacitance C. Now, in order to characterize the behavior of such a cable, such a Hermann cable, we look on the current that is flowing in the x direction. Now for the internal current, I of x, which is characterized by the inside resistance, is characterized by the voltage drop dV of x by dx at that place. Hence II is equal to minus, because there's a negative voltage drop, minus 1 divided by Re dV dx. On top, there is a current flowing across the membrane, which is due to the current through the membrane. Hence, the membrane current is equal to the loss of current along the axon. dII dx is equal to I membrane is equal to the voltage divided by the membrane resistance Rm. Now, combining these two equations, we obtain a second order equation in the voltage, reading that Rm divided by Ri, second derivative of the voltage of x with respect to the position, minus V of x is equal to 0. Now, the solution of which is an exponential decay of the voltage, where V of x is equal to the starting voltage V0 e to the power minus x divided by lambda, where lambda is the square root of the membrane resistance divided by Ri. Now let's fill in typical numbers, where for the axon, where Ri is very large, the typical length scale lambda is in the order of 3 millimeters. Hence, after 3 millimeters, the signal that you apply at the beginning of the axon will basically die out. Now, that is very different as compared to the transatlantic cable, where this lambda would be 100 kilometers. Now, so far we neglected the internal voltage supply due to the Nernst potentials. Now let's add this and also add the capacitance of the membrane. So if we look on the current along the x direction, then the equations will not change. So II is equal to minus 1 divided by Ri times the gradient in the voltage. It's only that the membrane current now also gets a capacitive part, where the gradient of the current in the x direction, dii by dx, is equal to V divided by Rm plus the capacitance times dV by dt. Now reformulating our equation, leading to a second order equation in space and first order equation in time for the voltage, reading Rm divided by Ri times second derivative of the voltage with respect to space x minus v of x is equal to Rm times c times dV by dt. Now reformulating, we obtain the linear cable equation, reading lambda squared by times the second derivative of the voltage with respect to space minus tau times the first derivative of the voltage with time is equal to the voltage. Now let's try to find a solution to this second order space-time differential equation. Well, a good idea would be to start with an ansatz, because we know already how the equation should look as a function of time only. So now we take the ansatz that v of x and t is equal to e to the minus t divided by tau, which takes care of the temporal part, times w of x and t. Now, using this ansatz and filling into the linear cable equation, we obtain that this second derivative of w with respect to x times lambda squared divided by tau is equal to the time derivative of w. Now you should recognize or realize the equation that we just had here is equivalent to the diffusion equation, where the diffusion equation reads d times second derivative of v with respect to space is equal to the time derivative of v. And the solution of which is just an exponential function, so Gaussian curve, e to the minus x squared divided by 4 dt times the prefactor 1 divided by square root of pi dt. Now combining, we now have an equation how the voltage changes with space and time along the axon, assuming this passive cable, and we will find that the voltage is proportional to 1 divided by square root of t times e to the power minus t divided by tau exponent of minus x squared divided by 4 lambda squared tau times t. The main information that we obtain from this solution is there is no wave-like solution. So all signals that we have as an input in the beginning will die off in space and time very rapidly. At a typical time constant of a few microseconds and at typical space constants of a few millimeters. Now the solution I showed is I didn't calculate the full prefactors for this differential equation. Here you see the full derivative of the voltage drop across the membrane, for which our main conclusion, namely that there is no traveling solution, still holds. So you see that as well as a function of distance, as well as a function of time, the signal will die out very rapidly. Now, from our considerations today, it became clear that the passive cable is not a good model and is missing an essential ingredient, which we will discuss next week. Yet I think we have already a good startup to describe the signal behavior along the axon. We characterized the membrane. We saw that there is a specific membrane resistance of 10 kilo ohm per square centimeter. Then the inside of the axon is characterized by also a specific resistance of 30 ohm centimeter, and the membrane itself has a specific capacitance of 0.4 microfarad per square centimeter. Now, all these values lead to typical timescales in the order of 3 milliseconds and a typical length scale of a signal die-out of 3 millimeters. Yet, what I mentioned, it does not explain a traveling wave. For that, we need to extend our model.